Hi everyone, welcome to AAAI conference for this year. Before we get started, I just want to say a quick thank you for my mentor at Columbia University, as well as the organizer and the sponsor for this event. For me, it's a great honor to be here, and I'm very excited to get the talk started. So with that being said, let's start with the motivation. Here's the motivation of our work. The original idea of explainable AI actually originated from the DARPA document. Specifically, we're referring to this particular trade off between effectiveness of explanation and learning performance, which is also known as predictive rate. So let's dive deeper into this chart here. X axis, that is going to be the explainability or effectiveness of explanation. The y axis is really how well your model does, also known as prediction rate. And these dots are each individual machine learning algorithms. The classical methodology, such as linear regression, you can think of that as falling on the bottom right corner of this graph, which means that we understand pretty well, it's explainable, but it probably doesn't really perform that well. So something down here, you can think of that as the linear model. As opposed to linear model, you could also have an algorithm up here that has a relatively high performance, but it's very challenging to explain what that model is. Something like that could be neural network. So the idea of xAI is really about solving this trade-off, in the sense that it's possible to bring an algorithm that performs well, that has a high prediction rate, to the right, which basically means we inject some sort of methodology such that we can make this algorithm interpretable or explainable. So with that being said, that brings us to the three proposed conditions for something to be called explainable or interpretable. Right off the bat, the first thing I want to mention is our work is based on supervised learning. So in other words, we're talking about is you need to know exactly what that y is, and you need to have a clear target. So for example, if it's a classification problem, then you have your label. So that brings us to the first premise or the first condition, C1. It states that the feature selection methodology do not need to require the knowledge of the underlying model of how explanatory variables affects the outcome variable. So in other words, let's say you have your variables x, and then you have some sort of model f. Both of the x and f form together. That could be how you form the predictor. So your y hat is going to be f, you plug in x, something like that. This type of framework is good, but it's parametric. Basically means you have a model. Now here's a problem. If your y hat is wrong, so you have some sort of question that you're uncertain that if this thing is correct or not, how do you know that where the error is? Is the error falling on X or is the error falling on the model? So you cannot really trace back exactly where the problem is if you have a parametric procedure, which is why we say the first condition is really about non-parametric. So you do not require the knowledge of the model. Second condition says that an explainable and interpretable feature selection method must clearly state to what degree a combination of variables influence response variable. In other words, this x doesn't have to be just one variable. It could, as a matter of fact, be a set, right? x1, x2, x3, etc., something like that. And a measure needs to take this x and map this x onto a numerical number. So in other words, what we're trying to propose is a map to map x to the positive real line, in the sense that this gives you a score. So a score is numerical values such as 1, 2, 3, da 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 da. And this is great because it gives us a comparison, right? If we can say some value is 3 and some value is 2, we know that 3 is greater than 2. So that is the second condition. Now, the last condition is a little unique. It's actually related to the predictivity. So in order for feature assessment and selection technique to be interpretable and explainable, it must directly associate with the predictivity of the explanatory variable. Now, in a sense, we're talking about the base error. So Base error rate you can kind of think of as something that's related to the base probability. So what is the probability such that you give me x, I can tell you the exactly which class this picture falls in, if it's a cat or if it's a dog. So in a dream world, when you have all of the information, when you know the population distribution, then you can maximize this. So this is how correct your model is. Now, the error rate is the complement of that. So you take 1, subtract, and essentially this formula is going to be the base error rate. So predictivity is really just the complement of that formula. Essentially, what we're proposing for this third condition is to tie this explainability methodology with the predictivity of the explanatory features. So with that being said, we can take a brief look of this table here of some of the existing methodology in the literature. The first methodology is CAM. CAM is short for Class Activation Map, CAM. And the first thing about CAM is it draws the heat map or saliency map of where neural network sees. So imagine you have a picture like that, and perhaps you have a face of a cat. Then CAM is able to pinpoint the highlighted area on the picture so that it shows you where neural network makes that prediction. Now the problem is, for CAM, it actually required the internal access of the neural network. So then the question is, if the neural network is wrong, then CAM doesn't really do anything good, which means the first condition fails to check. The second condition requires CAM to be a quantifiable measure. Now if you draw a picture and that's a face of a cat, and you have a color highlight here, I can't really tell which pixel is more important than the other one. Or more importantly, you can also tell which cluster of area is more important than the other one. That remains unanswered, which means CAM fails to check the second condition. Now with that being said, it brings us to the last condition, which CAM also fails to check, because CAM by itself has nothing to do with the predictivity of the explanatory variables. So that is what we know about CAM. It's actually a very famous methodology and is considered as one of the go-to methodology if you want to do xAI. And on top of that, you also have LIME, which is really a linear analytics model. But again, it fails to check the first one because it requires linearity. The second one, you can actually do it because LIME actually gives you a feature score, which allows you to make comparisons. However, LIME doesn't really have anything to do with predictivity. So unfortunately, the third condition also fails to check. Now, in addition to CAM and LIME, we also have RISE, which is short for Randomized Input Sampling for Explanation, RISE, RISE. RISE fails to check the first one and the third one, but indeed it gives you some sort of measure, so it checks the second condition. So that is what we know from literature. On top of that, you might also ask a question, how about Sharpe value? Well, Sharpe value actually looks at each subset of the power set, so it can actually blow up in dimension, and I've actually never got the luck to try out Sharpe value on image data simply because it's a high dimension for Sharpe value. Let's say you have a picture that is 28 by 28 and this number is 784 pixels, then Sharpe value, it really looks at 2 to the power of 784 because that's a power set of partition that this feature space can generate. So this is actually an insanely amount of number that I'm not even sure if the modern day technology can make that computation. So for Sharpe, I was actually never able to test out all these conditions. With that being said, that leads us to I-score, which is the highlight of our work. So specifically in this talk, I'm going to bring you guys through the definition of I-score and explain what is an interaction-based study. And in addition, I'm going to introduce how I-score can be implemented in convolutional neural network as well as recurrent neural network. So with that being said, let's start off by looking at the formula of I-score. This is the formula for I-score in a discrete sense. So we are assuming that all of x is taking value of 1 and 0. And what that means is for each x, you have two partitions. Say you have x1 takes value of 1, 0, and x2 takes value 1, 0. Then together you have 2 to the power 2, that gives you 4 partition. And the partition concept is really important because that forms the basis of the I-score formula. And since this is 4, then this summation really adds up to 4. So in other words, this J is a rounding index that tracks which partition you are in. So that's the rounding index for the summation. Inside of the summation, we have a couple of things. We have nj square, yj bar, and y bar. This y bar is the global mean. And essentially you take your y from your training data and you compute the average. So that's the global average. You also have this yj bar. This is actually your local average. So when we say local, it's dependent on this rounding index j, which essentially track the partition that the observation falls in. So once again, this j is referring to that j's partition. And this y bar j is referring to the local average only for the observation in that partition j. Okay, so this j is actually a very important concept here. The last piece is actually this nj square. This nj square is essentially saying in that partition j, we count the number of observation and then we take a square. So altogether we have these 3 pieces of information and that forms this summation. And outside of the summation, we also have the scaling factor. N is sample size, so that is essentially your sample size in your training set, and this Sn square is your variance. So essentially it's a variance of your response variable. So as you can see, I-score is really built and defined using both x and y. So in other words, it's a supervised measure. Now, with that being said, one important thing to use this I-score function is to combine it with this algorithm called the backward dropping algorithm, of which we notate with calligraphic letter B. I actually run out of space to put the algorithm here, but you can essentially see it in our paper. You can find the link to our paper on my website. But the intuition for backward dropping algorithm, you can think of it as a small upgrade from the stepwise backward, which is a standard procedure in variable selection. Now, in addition to I-score and backward dropping algorithm, we actually have a third proposal, which is called interaction-based feature engineer. Interaction-based feature engineer is proposing a type of engineering phenomenon such that we build additional input variable called x-dagger based on the local average y bar of that j's partition. So here, this y bar j that you see, this rounding index j, actually refer to the jth partition. So essentially this x bar is a consequence that is 100% coming from this technique called partition retention. So those are the tools that we propose. How do we use it? Well, the first thing to introduce is an interaction-based convolutional neural network. In convolutional neural network, we're essentially trying to build features that can learn information from images. An image is a 2-dimensional array. So you can kind of think of it as a matrix, 3 by 3, 4 by 4, 100 by 100, you name it. And if it's 3 by 3, we can simplify it by x 1, 2, 3, 4, 5, 6, 7, 8, 9. You can think of it as a picture with 9 pixels. The convolution operation suggests that you have a small window such as this, that's 2 by 2, and then you can apply the predefined kernel on top of this picture to create the features. So what do I mean by that is, for example, you can have an edge detector. So this edge detector, maybe it looks like 1, 1, 0, 0. It's essentially a 2 by 2 matrix that one column it's all ones and everybody else it's zeros. So this gives you the information on the left column. So if you have a picture here and then maybe you have a house that looks like that, then this left edge of the house, if there's any information, then that information will be able to be detected by this type of kernel. So then you may ask a question, well, what happens if you go to the top of the house? What if the pattern is horizontal? Then if that's the case, you need to define additional kernel that look like that. So that will solve the problem of the edge that is horizontal. So as you can imagine, if this thing, and so on and so forth. So now you can probably imagine, to be able to extract as much information as we possibly can from the pictures, we need as many of these kernels as we can. And that's exactly true. Modern day CNN or deep CNN, they use a lot of these filters, which creates many parameters. So what we're proposing is we say, hey, in this 2 by 2 window, how about we don't use kernel? We use non-parametric methodology that we proposed, and we use backward dropping algorithm to read in these features, and then we can rely on I-score to tell us which one of them is important. Let's say the first small window, that's 2 by 2, we're talking about x1, x2, x4, x5. We throw the set of features into this backward dropping algorithm, and perhaps you produce x1 and x4, and that's going to be a set. And then this x1, x4 goes through the dagger technique, give us the first x1 dagger. And this x1 dagger can be essentially flattened out, and then you can essentially throw that as a neuron into the neural network architecture, and that gives you the first predictor. We can do that by going to the second window and throw that into the backward dropping algorithm and select the new variable set that goes to the x dagger to create x dagger 2. This x dagger 2 now comes to here, becomes the second predictor. And you do this so on and so forth, it will eventually give you a new convolutional layer. And this forms the predictor space. And we use these predictors instead of the original pixels to form that final prediction. This formula here is essentially a shorthand notation for how you construct one neuron. Instead of this, it's a linear additive formula, and then you throw that into an activation function. And that will essentially give you this y hat. So we propose this design as an upgrade of the classical convolutional layer, and it turned out that this design can actually be generalized into recurrent neural network. If you are doing natural language processing, or if you're working on time series data, it can actually be generalized. So how do you generalize, you may ask? Well, instead of a two-dimensional array, we're looking at a one-dimensional vector because it's time series. So these x1, 2, 3, 4, 5, 6, 7, 8, you can think of this as the timestamps. And every small window is going to be a vector of, say, 5 variables. So maybe you have 1, 2, 3, 4, 5. And you throw these 5 variables into the backward dropping algorithm, you go to the dagger technique, it will give you this first x1 dagger. And then you can rotate to the next word or next time series data, starting from x2. Now you're going to have 2, 3, 4, 5, 6. That gives you the next set of parameters that you can throw in the backward dropping algorithm to produce that x2 dagger. So essentially, so on and so forth, you can go through all the way in the end until you hit 4, 5, 6, 7, 8, and you can essentially recreate a new interaction-based layer based on the original predictors. Now these x daggers 1, 2, 3, 4 have compact information that is distilled and extracted from the original sample space, which, as you can see, it's a much higher dimension, x1, 2, 3, all the way to 8. So this is the architecture that we're proposing. And to give you a vivid example, let's talk a little bit about the chess xray dataset. So this is a well-known dataset in a sense that many people have done a good amount of research on this dataset. And if you look at just 2 classes, say you're trying to predict pneumonia, you can actually get to 98 or even 99% if you're just using a dense net or some form of deep CNN. But the problem is, how do we trust that? And if we can't trust it, how do we deploy it? So our work here is really to build upon the methodology that we have to deliver the high prediction rate, but we also want to inject explainability. So first things first, we process this data as a two-dimensional picture, and then each small area, let's say a 2 by 2 window, what do we have? We have 4 pixels. So 4 pixels, you can think of it x1, x2, x7, x8. Obviously, these indexes are just examples. Then you start your backward dropping algorithm. So you iteratively drop each one of these variables, you track the I-score. If you happen to drop this variable x8, that I-score happen to increase the highest, then this x8 is going to be the variables that you drop. And the reason is because had you dropped that one, the remaining set of variables x1, x2, x7 have the highest I-score. So then that means this is the bad guy and you don't want that. You do the same thing, you iteratively drop one of these x1, x2, x7. It turned out that if you drop x7, the I-score is the highest, which means the remaining variables is more important. And you keep going until you have nothing to drop, and all the way in the end, you look across the board, you see which I-score is the highest. The I-score that is the highest will give you the predictor space that is the most important. In this case, it's a set of variables that's x1 and x2. This x1 and x2, we're assuming that they're both binary, so we're talking about 1, 1, 1, 0, 0, 1, 0, 0. That's the sample space. Because it's 2 by 2, that's 4. Then we can compute the local average. Hence, we have y bar 1, 2, 3, 4. And these 1, 2, 3, 4 is referring to the partition. So once we have this local y bar from training set, we can construct this x1 dagger. Then this x1 dagger will now have a compact information combining the power of x1 and x2. And this x dagger will then be parsed to here while maintaining the same geographic location of the pixel. So that is how we're able to shrink the dimension of a picture from size, say 128 by 128, all the way to 14 by 14. Because as a matter of fact, you can actually do this motion more than one time. So once you shrink to 14 by 14, now you can actually see these little pixels here. You can flatten them out, and then you can fully connect them. You can make your final prediction. So that is the procedure for making predictions. Now we can also take a look at a little bit of an inference. So if you watch carefully, this picture here, 14 by 14, some of these pixels on the edge, they are green color. Some of them in the middle, but not in the center, they're probably blue or purple, and the ones in the dead center, they are probably red. So you might ask, hey, what does this color coding mean? We plot the color palette down here. You see two color palettes that are completely identical. The first one is I-score. The second one is AUC in percentage. In terms of color palette, they're completely identical. If it's green here, then it's green here. If it's purple here, then it's purple here. But what's different is the value. AUC is a percentage. If you're coming down to the left end of a scale, then AUC is about 60% or shy of 60%. If you go to the right end of a scale, you see purple bar here, that AUC is above 80%. So it's relatively high. Essentially, we're talking about these pixels here. Even just one pixel by itself already delivered an 80% AUC, which is extremely informative. Now, what's the interesting thing here is the same pixel, not only can you compute AUC, you can actually also compute I-score. So this one pixel here, you can do two things. You can compute I-score, or you can compute AUC. Now, the interesting phenomenon here is I-score actually shares similar pattern with AUC. If I-score goes up, AUC has to go up. If I-score go down, AUC has to go down. And we can see that because they share similar color palette, and they go up, go down together. But what I-score is doing a little bit better is the extremely predictive area. We're talking about that one bar that is living on the extremely right of this color palette. For AUC, you probably won't be able to see much because this increase is very marginal. Maybe we're talking about from 80% to 82% at best. However, that is not the case for I-score. For I-score, you are actually able to exponentially increase if that predictor is extremely informative. This additional information will not be captured by AUC, which is the power of I-score. So with that being said, I think two things that we can take away from this graph is, first of all, the higher the I-score, the higher the AUC. Second of all, if you're extremely predictive, I-score can detect it, but AUC is questionable. So with that being said, now we can take a look at the performance. Let's take a look at the results first. So you can take a look at the benchmark. This is, by the way, 4-class classification. 4 classes are healthy. Class 1 is COVID-19, that's type of lung cancer. Class 2 is pneumonia. Class 3 is tuberculosis. So these 3 things are 3 different types of lung cancer, and they're testing against healthy classes. So in this 4-class classification, you can see the best we can have is 94%, and that probably needs 40 million parameters in your neural network. However, if you use a proposed methodology, you can essentially get a few percentage better, but with much less parameters. In the sense that you can essentially use an average of 15,000 parameters that you can get a few percentage better. And that's the explainability that we want. That's what makes this methodology explainable. In addition, we also have this nice graph here. The first column is the original pictures. Here we have 4 different samples coming from a different class. The first one, obviously, that's true label is healthy, and we test that against 4 different models because there are 4 different classes. And you are really not supposed to see anything because it's a healthy person. Now, the second picture, the true label is class 1, which is the type of lung cancer caused by COVID-19. And if you test out against all 4 models, you're going to see yellow highlight here. That is going to be for this class of disease, which is great because not only do we have high performance, we also know exactly where the disease come from. You probably also notice some area here on the edge, some area here in the stomach area, and it's not perfect, right? That's probably because we suspect that in the data set, there's a little bit of imbalanced distribution going on. Somehow the person with this type of disease, maybe there's something going on with the stomach as well. That's definitely possible. So the next line, we have this picture that's coming from class 2, which is just straightforward pneumonia. And if you can take a look at all of the models, obviously the filter that's for pneumonia, which is class 2, shows up some sort of highlight, which is extremely important. And the last one, true label 3, for tuberculosis, this will essentially also give you some shaded area or highlight for your lung area, pinpointing exactly where the problem is coming from. And everything else, there shouldn't be any highlight. So that's the story here that we're trying to propose. Now, this type of pipeline is extremely helpful because not only do we predict high performance and learning high prediction performance, we are also able to tell the end users, the doctors, the subject matter expertise, the location of the lungs that they should be investigating, which can actually make the entire treatment pipeline much more efficient. So with that being said, that wraps up our talk today. Thank you all for listening. I'm extremely grateful for this opportunity and happy to connect with all of you on LinkedIn. Hope you enjoy the rest of the conference. Have a nice day.